Welcome back to our ongoing deep dive into mathematics. Last time we wrapped up looking at
Oh, yeah.
knot theory.
That was fascinating.
It was. Today we are venturing into stochastic calculus.
Oh, right. Which sounds
It's
a little intimidating.
a bit intimidating, I know, but I promise it's got surprisingly relevant applications
It really
in
does.
so many areas.
Absolutely. Stochastic calculus is basically a way for us to apply the power of calculus
Okay.
to systems where randomness is just something you can't avoid.
Hmm.
So instead of those nice, smooth, predictable curves that
Hmm.
you might be used to, we're dealing with unpredictable jumps and fluctuation.
Okay.
Things like stock prices, the movement of molecules,
Yeah.
weather patterns.
So it's calculus for the messy real world where things don't always behave
Exactly.
like nicely.
Yeah, it's a calculus.
But I remember from my calculus classes,
Mm-hmm.
like everything was about those smooth, continuous changes.
Right.
How do we even begin to apply calculus to something that's inherently random?
That's a great question.
Yeah.
And that's really where things start to get interesting.
Okay.
We have to kind of bridge the gap between the world of discrete individual events
Okay.
and the world of continuous processes.
Okay.
So let's start with something simple.
Okay.
Imagine a basketball player shooting free throws.
Okay.
Each shot is a separate event
Yeah.
with a probability of success or failure, right?
Right. And we could use something like the binomial distribution
Exactly.
to figure out the chances of them making a certain number of shots
Yeah.
out of, say, 10 attempts.
Exactly. That's a classic example of a discrete system.
Okay.
But what if we want to analyze something that's constantly changing, like the price of a stock over time?
Right.
Those discrete tools kind of start to break down
Yeah.
because the price isn't jumping in neat, predictable steps.
I see. So we can't just rely on simple points and sums
No.
to analyze something that's constantly fluctuating.
Yeah.
We need a way to handle those continuous changes.
Precisely. And that's where calculus comes in.
Okay.
But we have to think about those discrete events like those coin flips
Okay.
or the free throws
Right.
in a slightly different way.
Okay.
Imagine taking those coin flips,
Mm-hmm.
shrinking them down,
Okay.
and making them happen more and more frequently. What happens to the overall shape?
Well, if I picture those coin flips piling up
Yeah.
as we make them smaller and more frequent,
Yeah.
it seems like it would start to resemble a bell curve.
Right.
A familiar shape of a normal distribution.
You got it.
Okay.
And that transformation is hinting at a powerful concept called the central limit theorem,
Okay.
which tells us that if you add up a bunch of independent random variables,
Okay.
even if they're not normally distributed themselves,
Yeah.
their sum will tend towards a normal distribution
Okay.
as the number of variables increases.
That makes sense, but we're still talking about
You're right.
discrete events,
Yes.
those coin flips.
Yes.
How do we make the leap to a truly continuous process?
Yeah.
Like the movement of a stock price.
We imagine those coin flips happening so rapidly,
Okay.
with the time between flips becoming infinitesimally small,
Okay.
that it essentially blends into a continuous process. And that brings us to the concept of Brownian motion.
Brownian motion. I
Yeah.
remember hearing about that in science class.
Yes.
It's the random movement of particles in a fluid, right?
Exactly, like dust motes dancing in a sunbeam.
Right. Yeah.
Exactly. And it's a foundational concept in stochastic calculus.
Okay.
Brownian motion is continuous, meaning its path doesn't have any gaps.
Okay.
But it's also incredibly jagged and unpredictable.
Okay.
In fact, it's so jittery that we can't calculate its derivative using the regular tools of calculus.
So we need a new set of tools to handle this kind of chaotic movement?
Yes.
That sounds like where things might get really complex.
That's where Ito calculus steps in.
Okay.
It offers a new set of rules for working with these unpredictable paths. And it introduces a pretty mind-bending twist.
Okay.
In standard calculus, the square of an infinitesimally small change,
Okay.
like D'Ito square,
Yeah.
is basically negligible. It's so small we can ignore it.
Okay.
But in Ito calculus, the square of the change in Brownian motion, represented as dw squared,
Okay.
actually matters. It doesn't vanish as the time interval shrinks.
Wait, why is that?
Yeah.
Why would the square of a change be significant in Ito calculus,
Yeah.
but not in regular calculus?
It all comes down to the nature of Brownian motion.
Okay.
It's constantly fluctuating, so even though each individual change is tiny,
Right.
they add up in a way that standard calculus doesn't quite capture. And this seemingly small difference has huge implications
Got it.
for how we calculate and model these systems.
So this dw squared thing is really important.
Yes.
But how does this new type of calculus, Ito calculus,
Right.
actually help us in practical terms?
Yeah.
What kinds of problems can it solve?
Ito calculus is the foundation for a really powerful tool
Okay.
called stochastic differential equations, or SDEs.
Okay.
And these equations are used to describe systems where there's a combination of predictable trends and random fluctuations. So think about a stock price.
Okay.
It might have an overall upward trend,
Right.
but it's also going to experience daily volatility.
Ah, so an SDE can capture both of those elements,
Yes,
the steady growth and the unpredictable jumps,
exactly.
making it much more realistic than a simple equation that just describes
Yeah.
a straight line upward.
Exactly. It's like we're creating a mathematical language
Yeah.
to describe the messiness of the real world.
Yeah.
And it turns out that Ito calculus isn't the only approach to stochastic systems.
Oh.
There's another method called Stratonovich calculus
Okay.
that offers a slightly different perspective.
Interesting.
Yeah, that's right. Ito calculus has been incredibly useful.
Yeah.
But it's not the only game in town
Right.
when it comes to dealing with this randomness.
So when would we choose Stratonovich over Ito?
Right.
What kind of problems?
Yeah. What makes one a better fit than the other?
Yeah.
It often comes down to the specifics of the system that we're trying to model.
Okay.
And the type of noise that's involved. Stratonovich calculus is really good at preserving symmetries
Okay.
that are often found in physical processes. So it makes it a good choice when we want our model to accurately reflect
Yeah.
the underlying physics.
Okay.
It can also be a more natural fit
Okay.
when we're dealing with noise that's not perfectly white, meaning it's not completely random
Right.
and uncorrelated, like pure Brownian motion.
So in the real world, where noise is often a bit messier
Exactly.
than the ideal Brownian motion,
Yeah,
Stratonovich might have an edge.
exactly. And there's actually a theorem called the Wang-Zakai theorem
Okay.
that formalizes this idea. It tells us that if we approximate this smoother real-world noise
Okay.
with increasingly fine approximations of white noise,
Mm-hmm.
the resulting stochastic differential equation actually takes the Stratonovich form.
Fascinating. It's like we're getting a glimpse into how mathematicians connect
Yeah.
the abstract world of pure math with like
The real
the
world.
more nuanced complexities of the real world.
Yeah.
So if we're dealing with a system where we want to preserve those inherent symmetries,
Yeah.
or if the noise isn't perfectly white,
Right.
Stratonovich calculus might be the way to go.
You got it. It's about choosing the right tool for the job.
Right.
And speaking of choosing the right tool,
Yeah.
Stratonovich calculus also shines in certain areas like stochastic control.
Stochastic control, that sounds like a whole other
It is.
layer of complexity.
It is.
What does that involve?
Imagine you're designing a system
Okay.
that needs to operate in an environment with unpredictable elements,
Huh.
random disturbances, fluctuating inputs,
Okay.
that sort of thing.
Yeah.
Stochastic control is all about making decisions
Okay.
and designing control strategies
Mm-hmm.
to guide the system towards some desired outcome,
Right.
even in the face of all that randomness.
So it's like navigating a ship through a stormy sea.
Yes,
You have a destination in mind,
right.
but you need to constantly adjust your course to deal with
Exactly.
the unpredictable waves and winds.
That's a great analogy.
Yeah.
And Stratonovich calculus can often simplify the equations involved in these stochastic control problems,
Okay.
making them easier to work with and solve.
Right.
It provides a more elegant framework for
Okay.
dealing with those unpredictable elements.
It's amazing how these mathematical
Yeah.
tools can be applied to such a wide range of problems.
Is.
We've talked about finance physics now, control systems.
Yeah.
Are there other fields where stochastic processes play a key role?
Absolutely. They pop up in really unexpected places. Like, take biology, for example.
Okay.
Think about a tiny bacterium swimming through a fluid.
Okay.
It's constantly being bombarded by water molecules,
Right.
which cause random fluctuations in its movement.
So we could use a stochastic process to model the seemingly chaotic path
Precisely.
of that bacteria.
Exactly. And the choice between Ito and Stratonovich
Right.
could be crucial here as well.
Okay.
Stratonovich often aligns better with the physical laws
Okay.
governing that bacterium's diffusion. So it ensures that our model reflects the actual reality of the situation.
It's like we're using these mathematical tools to like zoom in
Yeah.
and understand the microscopic world where randomness reigns supreme.
And it doesn't stop there.
Oh, wow.
Stochastic processes are used to model population dynamics, the spread of diseases, even the firing of neurons in the brain.
Wow.
They're a fundamental tool for understanding complex systems
Okay.
across many different scientific disciplines.
This is really highlighting the power of stochastic processes.
It is.
It's not just some niche area of math.
Yeah.
It's like a way of thinking
Right.
that allows us to grapple with uncertainty and randomness
Yeah.
in a rigorous way.
Couldn't agree more.
Yeah.
And as we explore further, we'll see even more connections and applications
Okay.
that showcase the elegance and utility of stochastic calculus.
Hmm.
But for now, let's take a step back
Okay.
and revisit something we touched on earlier.
Yeah.
The idea of discrete random walks
Okay.
and their connection to continuous Brownian motion.
Yes. That was a great way to start bridging the gap
It was.
between those two worlds.
Ugh.
How does that tie into the bigger picture of stochastic calculus?
Well, it turns out there's a fascinating connection
Hmm.
between stochastic processes and a mathematical concept
Okay.
called score code space.
Score code space. That's a new one.
It is.
What is that all about?
Think of it as a special type of mathematical space
Okay.
that's designed to handle functions
Okay.
that are right continuous with left limits.
Okay.
They're often called Cadlag functions,
Okay.
which basically means they can jump at certain points in time,
Okay.
but stay constant between jumps.
So like a staircase, but the steps can happen anywhere along the way.
Exactly.
Okay.
And these catalog functions are perfect for describing processes
Hmm.
that evolve in this kind of jumpy, discontinuous manner.
Okay.
Which is often the case
Right.
with stochastic processes.
Okay, I'm starting to see the connection.
Yeah,
But why do we need this special score code space
right.
to deal with these functions?
It provides a natural setting for studying and analyzing
Okay.
these jumpy catalog functions.
Right.
And here's where it gets really interesting.
Okay.
Many important stochastic processes, like Poisson processes and jump processes, can actually be viewed as random elements within this score code space.
Okay.
It's like we're organizing these jumpy processes
Right.
within a mathematical framework that makes sense
Right.
for their behavior.
So score code space is like a specialized tool
Yes,
for dealing with the kinds of unpredictable jumps and fluctuation
it is.
that we see in so many real-world systems.
You got it. It allows us to go beyond
Okay.
the smooth, continuous world of traditional calculus
Yeah.
and create mathematical models that capture
Yeah.
the inherent randomness and discontinuity of many natural phenomena.
This deep dive is really opening my eyes to the breadth and depth
Good.
of stochastic calculus. It's much more than just a collection of equations.
Yeah,
It's a way of thinking about and modeling the world
it is.
that embraces uncertainty and complexity.
I couldn't have said it better myself.
Yeah.
And as we continue to explore this field,
Mm-hmm.
we'll discover even more fascinating connections and applications
Okay.
that demonstrate the remarkable power of mathematics to
Okay.
illuminate the hidden order within these seemingly chaotic systems. Ready to delve a little deeper?
Absolutely. It's clear that stochastic calculus isn't just about these abstract equations.
No.
It's really a powerful tool for understanding the complexities of the real world.
It is.
Before we were exploring score code space
Yes.
and how it helps us model those junky, discontinuous processes that we encounter so often.
Yeah, and it's amazing that we have these tools like score code space
Right.
to be able to handle these less conventional types of processes. It really expands our capabilities
Yeah.
beyond that smooth, continuous realm
Right.
of traditional calculus.
Like we're constantly adding new tools to our mathematical toolkit
we
to
are.
tackle even more challenging problems.
Absolutely.
Speaking of expanding our toolkit,
Mm-hmm.
are there any other surprising areas where stochastic processes have made an impact?
Definitely one area that's been particularly exciting
Okay.
is the field of machine learning, specifically a technique called score-based generative modeling.
Okay.
Leverages the power of stochastic differential equations
Okay.
to create new data samples.
Wow, that sounds fascinating.
It is.
Could you break down how that works?
Yeah,
I'm having trouble picturing how we can use equations to generate something new,
right.
especially with all this randomness involved.
Imagine you have a data set of images, for instance.
Okay.
Score-based generative modeling uses those stochastic differential equations to describe how noise evolves over time.
Okay.
And by carefully designing those equations, we can essentially guide that noise to gradually transform into images that resemble the ones in the original data set.
So we're starting with pure randomness
Right.
and then using these equations to sculpt that noise into something meaningful.
Kind of like that.
It almost sounds like magic.
Yeah, it's a bit like that.
And what's remarkable is that by reversing this process,
Yeah,
we can generate completely new images
right.
that share the same statistical properties as the original data set,
Exactly.
even though they weren't part of the training data.
That's right.
That's mind-boggling.
It is pretty amazing.
Like, we're teaching machines to be creative
Yeah.
by harnessing the power of stochastic calculus.
It is.
It opens up a whole new world of possibilities.
It does, and that's just one example.
Wow.
Stochastic processes have also made their way into epidemiology,
Okay.
where they're used to model the spread of diseases, queuing theory to analyze waiting times and optimize resource allocation,
Right.
and even material science to study the behavior of particles at a microscopic level.
It's truly incredible how this field, that might seem abstract at first glance,
Yeah,
has had such a profound impact on so many different areas
I know, it's really cool.
of science and technology.
It is.
It speaks to the power of mathematical modeling
Yeah,
by finding the right mathematical framework
yeah,
to describe a phenomenon.
yeah.
We can gain these profound insights into its behavior,
Mm-hmm.
make predictions, and even design strategies
Yeah.
to influence or optimize it.
Exactly.
This deep dive has been an incredible journey
It has.
into the world of stochastic calculus.
It's been a lot of fun.
We've covered so much ground,
We have.
from the fundamental concepts of Brownian motion and Ito calculus
Yeah.
to the nuances of Stratonovich calculus and Stochastic space.
Mm-hmm.
And we've explored applications ranging from option pricing
Yes.
to machine learning and beyond.
Absolutely. It's been a pleasure sharing this exploration with you.
Yeah.
I hope our listeners have gained a deeper appreciation
Yeah.
for the beauty, power, and remarkable versatility
Mhm.
of this field.
Absolutely. It's clear that stochastic calculus isn't just a niche area of mathematics.
No, it's not.
It's a fundamental way of thinking about the world
It is.
that allows us to grapple with uncertainty
Yeah.
and find patterns within these seemingly chaotic systems.
Beautifully said.
Yeah.
And as we wrap up this deep dive, I want to leave our listeners with one final thought to ponder.
Okay.
We've discussed how stochastic calculus helps us model and analyze random events.
Right.
But what about the very nature of randomness itself? Is it truly unpredictable?
Yeah.
Or is there some underlying order that we haven't yet grasped?
Yeah.
It's a question that has captivated thinkers for centuries,
Right.
and it continues to drive new research and exploration
Yeah.
at the frontiers of knowledge.
That's a truly thought-provoking question to leave us with.
I hope so.
It seems our journey into the world of stochastic calculus has just begun.
It really has.
Thanks to everyone for joining us on this deep dive
Yes.
into the captivating realm of stochastic calculus.
Thank you.
Until next time, keep those minds curious
Mm-hmm.
and never stop exploring the wonders of mathematics.
It's been a pleasure.